Well, hello and welcome to Doc Onco Physics. Keith Onco here. What we're going to be doing today is taking a look at the second part of rotational dynamics. We've taken a look at the first part already, which is rotational dynamics and how we do kinematics analysis. And today what we want to do is we want to take a look at rotational dynamics, things that are spinning about their own axis, and something called torque. Okay. If you remember looking back in the rotational dynamics kinematics lesson, or any of the problems that we've done, there are equivalent formulas, variables, equations in the linear world as to there are in the rotational or spinning world. Okay, and one of those things is torque. Okay, and torque is spelled T-O-R-Q-U-E. And what torque is the equivalent of a force. Okay, so we have force in the linear world, and we have something called torque in the rotational world. Okay, and one of the examples I always give is let's say you have a door, which is pictured to the left, and you have got a door handle, and where is it you intuitively always push the door? Right? The hinges are over on the left-hand side, so there's, say, a hinge there and a hinge there and a hinge there that you can't see because they're probably on the other side of the door. But intuitively, you always push the door as far to the opposite side of the hinges as you can. And why is that? It just happens to be easier. All right? And so what we do is I have students come and apply a force out here at that location. Then I have them apply the same force in the middle of the door, and then the same force close to the edge of the door where the rotation would be, or the pivot point, or the hinges on the left-hand side. And what all of the students find invariably is that it is much easier to get the door to rotate if they push with a force on the outside of the door than if they push here. And if they push here, in many cases they can't even get the door to open at all. Okay, and so anytime we're going to rotate an object, all right, and we're going to get an object to spin, and indeed the door is spinning, then we're not just going to look at force, or we can't just look at the force applied to the object that we're trying to rotate about a central point, but we have to talk about something called torque. So the distance from the hinge, if this is the hinge here, the distance from the hinge makes a difference. Okay? If we were to look top down on the door, say this is the center point over on the right-hand side, what would happen is if we push the door with a force right about there, what could happen is the door would start to rotate back, and it would keep going back, and it would keep on going along a circular path until something stopped it. And in fact, if you've ever been to a hotel or a large office building, sometimes they have those rotating doors as you enter the lobby. They're supposed to be more heat efficient, and those doors just will keep on going around in a circular path. So if you keep pushing at the edge of the door, that door will continue to just go around in one big circle. Okay, and so the door is traveling in a circular path about a central access point. In order to get the door to move, or any object to move, in a path like this, we have to apply a force, but we're going to apply the force at some distance, right? Some distance here from the center of rotation. This center of rotation is something I call a pivot point, and sometimes it's called a fulcrum, especially when we're talking about something like a seesaw. It's a fulcrum. But I call this a pivot point, and it is the center of rotation for the object that is going around in a circular path, all right, for the edge of an object going around in a circular path. Okay, so What's the equation for torque? Well, since this is physics, there's always an equation. If you look over on the left-hand side, we have one equation for torque, and we'll have another one later on in this session. And it is this. It is the force applied to an object, all right, or somewhere in the object, times the distance from the pivot point, all right? And this distance from the pivot point is sometimes called a lever arm. Okay, lever arm. Okay, lever arm is what R would be. F would simply be the force. And we also have to apply the sine of some angle, because we can push this door in a variety of ways. I can push it like this and probably get the most out of my force. Okay, but what if I pushed the door like this, right? So I still applied a force to it, but I pushed it on the edge. Would that door begin to rotate at all? Well, the answer is no, it wouldn't, right? In order to get the door to rotate, some component of my force is going to have to be perpendicular to this thing called the lever arm right there, okay? And so we could, if we wanted to, find out the components of the force, right? But instead of finding the components of the force, we just add this one component to the equation. It is the sine of the angle. So let's take a look at that. If this is, I'm going to draw this in another color here. Let's go with blue so I can overwrite this. Let's say I have a force here, all right, and it's the new blue or purple force there, and I'm applying it like that. Well, what's the force relative to my lever arm? Well, here's my lever arm. Right? What's the angle of this force right in here? Well, this is 90 degrees. Okay? What's the sine of 90 degrees? Well, the sine of 90 degrees is 1. Okay? And that's the greatest value the sine function can ever have, is 1. So I'm going to have the maximum effect, right, from a torque perspective if I push on the door in a perpendicular fashion to this lever arm here, all right? Now let's say I pushed on it like this, okay? Well, what angle is that? Well, that angle is 180 degrees, okay? The sine of 180 degrees is a big fat 0. So the sine of 180 is equal to 0. Am I going to get any torque out of that? I am not. Okay, it doesn't matter how big a force I push on it with, I'm not going to get any torque. Okay, and then of course there are angles all in between. All right, let's say that I push instead at some angle, and let's say that angle is something like this, and it's like 45 degrees. So here's the lever arm again. This angle in here, let's say, is 45 degrees. Well, now, the sine of 45 degrees I know to be 0.707, and so I'm going to have a component of the force that is going to be perpendicular to my lever arm, and that is going to add to the torque that I have, or impact the torque that I'm going to be pushing on the door with. Okay, so torque is equal to the distance from the pivot point times the force that we are acting on it with times the sine of the angle between the lever arm and the force itself. Okay, so that's what torque is. All right, and again, its analogy in the linear world would be force. Well, we also know that force is equal to mass times acceleration. Okay, well, we know that torque is equal to r times f times sine of theta, but if force is equal to ma, all right, and torque is the equivalent of force in the rotational world, well, what is the equation for torque then that would be similar to Newton's second law? Well, mass has its corresponding variable in the rotational world, and that is I, the moment of inertia, and acceleration has its component as well, its counterpart, and it would be alpha, and that's simply the angular acceleration of whatever it is that's being rotated. So as this door moves through here and accelerates, it can be accelerating with some angular acceleration alpha. Okay, the door itself is going to have a mass, right? But for rotating objects, it's not just mass that matters, but it is this thing called the moment of inertia. It's where the mass is placed on the object that's rotating. Okay, where the mass is makes a big difference when you are rotating an object. Okay, all right. So that's an introduction to torque. So let's do a couple of examples here, simple examples of how we can determine the torque on an object. And so we have two possibilities here, and they're both wrenches. And so we have a nut here, right? And we have a wrench over here. Let's change that to black. And we have two forces. We have a force of A and a force of B. And I'm going to say that FA is equal to FB, and they're both going to be, say, 12 newtons. All right, so they're both 12 newtons. However, the distance, right, from where A is applied to the center of rotation here is, say, let's say this is 15 centimeters from this point to this point. And let's say that it's 30 centimeters from the point of rotation out to this point. All right, so it's double the distance. All right, so what I would like to know is I would like to know the torque that we are going to generate if I apply the force at position A or if I apply the force at position B. Now notice that the angle between the force and the lever arm, this would be the lever arm here, right, is 90 degrees. So the sine of 90 degrees is 1. All right, and so my torque is going to be equal to F, which is going to be 12 newtons, times R, and so let's make this the torque of A. So for A, it's going to be 15 centimeters or 0.15 meters. All right, and when we do this math, what we come up with is about 1.8 Newton meters. Okay, and so that would be the torque that we would develop if we applied that force at position A. So let's look at the torque if we apply the same force at position B. Well, it's still going to be a force of 12 newtons. We're not going to increase that at all, but we're going to double the distance, right, from the center of rotation out to point B over here. And that's going to be 30 centimeters or 0.3 meters. Well, as you can easily figure out, we double the distance. This is a linear equation. We are going to double the torque, and so it's going to be 3.6 Newton meters. Okay, now, why did I not apply the sine of the angle, which I should have done, right? Because the angle here is 90 degrees. Sine of 90 degrees is just 1. So anytime that you have the force perpendicular to the lever arm, right? This force here is perpendicular to the lever arm. The sine of the angle, which is going to be 90, is just going to be 1, and so you can eliminate that part of the equation. All right, let's take a look now over at this example over here. And again, we have the same kind of situation. We have a nut over here, all right, and we have a force that's being applied right at this point, right out here, and this is 25 centimeters. Okay, but this time the force is being applied at 37 degrees, so it's not the optimal force. Maybe for some reason just couldn't apply the force in a perpendicular fashion, but you can only apply it at an angle. So the torque that's going to be applied is going to be the force, which is going to be 17 newtons, times the distance from the pivot point, which is going to be 25 centimeters or 0.25 meters, times the sine of the angle between them, which is 37 degrees. Well, when we do this arithmetic, here's what we get. See, the sine of 37 degrees is about 0.6, and we multiply that by 17 and then by 25, and we get, or 0.25, I'm sorry, and we get a torque equal to about 2.55 Newton meters. Okay, so 2.55 Newton meters. All right. Now, how do we know what angle to use here? How do we know whether to use this angle or this angle? All right, if I draw this straight line out here. Well, this is 180 degrees from here all the way to here. And so this angle in here is 180 minus 37, which would be 143 degrees. Okay? If you plug the sine of 143 degrees into your calculator, what you're going to get is 0.6. So the sine of 143 degrees is equal to 0.6. So it doesn't matter which angle you use, whether you use the 37 here or you use the 143, you're still going to get the same answer. So this is a very basic example of how to calculate the torque on a given wrench in this case. All right, so let's try one more example. And this example has to do with something called rotational equilibrium. Well, what is rotational equilibrium? Well, as you might guess, rotational equilibrium is when we have balance, rotational balance. In the case of a seesaw, the seesaw may be balanced, so it is not going down on that side, nor is it going down on that side, but both people who are sitting on the seesaw perfectly balance out the seesaw so it stays level. Okay? Technically, rotational equilibrium means that we're not increasing the velocity of the rotation in either direction, so there's no acceleration. If there's not going to be any acceleration, remember that torque is what causes acceleration, right? So torque divided by the moment of inertia is equal to angular acceleration. If there is no torque, all right, total torque on the object, then there's not going to be any acceleration. Well, so we'd like to find where we're going to have this thing called rotational equilibrium. Well, let's say this person over here was not on the seesaw. What would happen to the seesaw? Well, it's going to rotate in a clockwise direction until this edge of it here hit, I'll change this to red, this edge of it over here hit the ground somewhere. Okay, we'll assume that it can hit the ground. But with both people on the seesaw, we could achieve rotational equilibrium, but they're going to have to be sitting in different places. Okay, this is my pivot point right in the center, right? And so my pivot point is exactly at the center of mass or the center of gravity of my seesaw itself. So the seesaw will not add to the torque in either direction, but it's only the people who are sitting on there. And so if I want rotational equilibrium, the sum of the torques in the clockwise direction will need to equal the sum of the torques in the counterclockwise direction. Remember, clockwise is always going to be going in this direction, right? Think of the hands of a clock. Which way do they move, right? They move around in the direction of the minute hand or the second hand. Counterclockwise, well, it moves in the opposite direction, right? It's going to move like that. And I want to figure out which of the forces, when applied to the seesaw itself, will cause the seesaw to go in a clockwise direction, and which will cause it to go in a counterclockwise direction. So we need these to be equal in order for this to be balanced. Well, let's assume, well, we don't have to assume because it says it right here. The person on the right, who has a mass of 60 kilograms, is 1 meter from the pivot point, or the fulcrum. All right? So the clockwise torques are going to be this. We're going to have 60 kilograms times 9.8 meters per second squared, right? And that's the value of G. That gives us the force that this person is applying at that point right there, times, now the torque is equal, remember the force, this is the force, times the lever arm distance. Well, that's just going to be 1 meter because the distance from here out to here, right, is 1 meter. So 1 meter, right? And if we multiply both of those together, we get 60 kilograms times 9.8 meters per second squared times 1 meter, and that is 588 Newton meters in the clockwise direction. Okay, so we took that person, their mass, we multiplied it by the acceleration due to gravity, we got the force due to gravity, we multiplied that by the distance from the pivot point, and we get 588 newtons. Well, in the counterclockwise direction, what do we have? Well, we've got a 30 kilogram person, again, times the acceleration due to gravity. Now, we don't know the distance, so we're just going to give that a value of x. Okay, but we do know this. The clockwise and the counterclockwise are going to have to be equal in order for us to have rotational equilibrium. Well, let's set the clockwise side equal to the counterclockwise side. Let's find out what 30 times 9.8 is first. 30 times 9.8, and that is 294. So this is 294, right, newtons times x. So what do we have here? And I'm going to change the color so it's just a little bit easier to see. So I'm going to go up here, and I've got 588 Newton meters is equal to 294 newtons times x. And x, of course, is in meters. If I divide each side by 294, I can get the value of x where the person on the left is going to have to sit. And as you might have guessed, x comes out to be 2 meters. So this person has to sit exactly twice as far away as, so this person has to sit exactly twice as far away as this person, because the original person, the 60 kilogram person, has double the mass that the person on the left has. Okay, so this is rotational equilibrium. Again, to figure out, analyze how we do this, if I want rotational equilibrium, the torques in the clockwise direction have to equal the torques in the counterclockwise direction, the sum of them. There's going to be times where we may have more than one torque on each side. All right, we could have two people sitting over here. We could have another person sitting over here. All right, and we might want to know where we might have to place a box on this side to balance it out, because now we would have multiple torques. You analyze it in the same exact way. You find your clockwise torques, add them up. You find your counterclockwise torques, right? And you set your counterclockwise torques equal to your clockwise, and you solve for whatever variable it is that you're missing. Well, that's the rotational equilibrium torque lesson. I hope that helps. I'm going to be doing a variety of different problems. So come on back, look at the problems if you're still having issues. And again, I hope that helps, and hope you have a great day.